Alright, so this section 9.3 is basically the same concepts from 9.2, except instead of a population proportion, we're looking at the population mean. So again, it's just like chapter 8 where we looked at the two differences in each section. So um, we'll talk about the requirements in order to use our t-test basically is what we're going to be using. The requirements are the same as from chapter 8. We'll learn how to perform a significance test using a population mean instead of a proportion. You know, we'll compare how the difference between that and the confidence interval, and then we'll look at how to do it using paired data. So um, we'll do an example of that near the end of the video here. All right, so confidence intervals and significance tests for population proportion B are based on z values from the standard normal distribution. So that's what we did last section. In this, we're going to use the t distribution with n minus 1 degrees of freedom. Remember, n is the number of our sample size, and so n minus 1 is our number of our degrees of freedom, because we're just looking. And just a little bit more detail about degrees of freedom. Basically, we're going to be looking at one statistic, and so that's why it's n minus 1. If we were looking at more statistics, we would have n minus a larger number. But that's since we're just looking at one statistic, it's going to be n minus 1. So again, this is very similar to 8.3, or the relationship between 9.3 and 8.3 is the same as the relationship between 9.2 and 8.2. All right, so we talked about this, I believe it was 8.3. A company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. So a simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Do these data give convincing evidence that the new batteries last longer on average? So our null hypothesis is that mu is still 30, and our alternative hypothesis is that mu is greater than 30 hours. So the same conditions that are required for carrying out a confidence interval are still true for when we're talking about a significance test. So has to be it has to be well designed random sample or experiment. If we're sampling without replacement, um, then it's got to be no more than 10% of the population size, um, and then basically it's got to be approximately normal or a large enough sample. And you'll see as we go through the examples that there's some latitude as far as what um, constitutes approximately normal. All right, so let's take a look. See whether we meet the conditions for for this battery example. So here we have our dot plot, a box plot, and a normal probability plot. Just to remember, it's been a while, but remember, if a normal probability plot is if it's linear, if it looks like a line, then it's approximately normal. All right. So first off, random. Well, it was a simple random sample, so it's random. 10%, we would assume that they're making at least 150 new AAA batteries, right? A single Costco pack has like 100, um, so you would assume they're making at least that many new batteries. And then is it a large sample? Well, no, n equals 15, so it's not bigger than or equal to 30. But if we look at the data, the dot plot looks slightly right skewed, I guess. Um, and same with the box plot. But the normal probability plot looks approximately linear, and so basically that's good enough to say, well, I think we can perform a test on this data. So how do we do that? So we do calculus assuming that the null hypothesis is true. Again, same as 9.2. So our test statistic is still the same formula. That's exactly the same formula from last time. The only difference is our standard deviation of the statistic is um, uh, using our sample mean. So we don't know the population standard deviation. If we did, we would use this guy, but usually we don't. So instead, we use this guy right here for our standard deviation of the statistic. So All right, so let's go ahead and do it. So we plug in our x bar is 33.9. Our null hypothesis, right? We're assuming that our null hypothesis is true, so mu is equal to 30. We plug that in, and then our standard deviation was 9.8 hours. That's again was given to us from the problem, and n is equal to 15 because our sample size is 15. So we plug that all in, we get t equals 1.54. Now, what we're going to do is we're going to look at that table. I believe it's table B, but it's in your AP formula sheet, or we'll also see how to do it on our calculator. But if we look at this, since we have 15, we're going to have 14 degrees of freedom, so df is going to equal 14. So that's why we go to this row, because it's n minus 1. Um, and we're going to look for where, basically we're looking for this number in the table. All right, so when I look at that, it's somewhere between 1.345 and 1.761, right? 1.54 lies between there. So I'm looking at somewhere, the p-value for this test is somewhere between 0.05 and zero point 0.1. So again, that's basically just saying, depending on what our confidence level is. Did we specify in this one what our confidence level was? I don't think we did. Um, no, we didn't. So um, we don't know what our alpha is. But depending on what it is, uh, if we want to be, again, um, oops, sorry about that. So but basically what it ends up happening is, the the probability, um, that this value is bigger than 1.54. So basically, the probability that this is a fluke or not is between 5 and 10% of the time. So this one, it would really depend on how like what our alpha value that we want to use would end up being. All right, so using table B wisely. So uh, basically one of the things is it only includes 1 to 30, and then it skips to 40, 50, 60, 70, 80, or sorry, 60, 80, 100. Whenever we're in those, what we're going to have to do is, like, if I have my sample size is like 55, then I'm going to have to round down and going to have to use like df equals 50 when I'm doing that if I'm using the table. Otherwise, um, we can we can use our calculators. We'll see that before the end of the video. And then also, just use symmetry. Table B only shows values for positive values of t. For negative value, just use symmetry. So we've done that quite a bit. All right, so this kind of talks us through how to use the calculator to do it. But so I can just go to, come on, so distribution TCDF. All right, so lower we had was 1.54. Upper we could do a big number. Again, you could just do like 10,000, or I always just do 1E99. Degrees of freedom, that was 14, I believe we were using. And so we go ahead and paste. Hit enter one more time. And remember, we said it was between 0.05 and 0.1. Well, here it ends up being 0.073, which is right where we thought it would be. And again, remember, like in 9.2, if we have a two-sided test, we would just multiply this number by 2. All right, so when the conditions are met, right, the approximately normal, it's a well-designed random sample or experiment, and the 10% rule. If those are all satisfied, then we can test a claim about a population mean mu using a one-sample t-test. So um, that's basically more or less what we were doing in the last example. So choose an SRS of size n from a large population that contains an unknown mean mu. Test hypothesis, the null hypothesis that mu equals mu naught. Compute the one sample t statistic using that formula. Again, it's just, remember, that's exactly the same as z-score. Um, remember it was the data point minus mu over sigma. Well, here our data point is our sample mean minus our population mean, which we do based on the null hypothesis. We assume that to be true, so we use um, we let mu equal mu naught, and then our standard deviation for a sample is s of x over square root of n. So um, and then find the p-value by calculating the probability of getting a t-statistic this large or larger in the direction specified by the alternative hypothesis. So our p-value again is basically this area right here. And again, that's basically that's the probability that the likelihood that we get the result we do or further from the mean, the population mean. All right, so here's an example, just giving us a bunch of data. This kind of uses quite a bit of stuff here. It's kind of a good example. So the level of dissolved oxygen in a stream or river is an important indicator of water's ability to support aquatic life. A researcher measures dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do we have convincing evidence at the alpha equals 0.05 significance level that aquatic life in this stream is at risk? And B, given your conclusion part A, which kind of mistake, a type 1 error or a type 2 error, could you have made? Explain what this mistake would mean in context. Okay, so let's just go ahead and state our problem. We want to test a claim about the true mean um, at the alpha equals 0.05 level. Our hypothesis are that, remember, our null hypothesis, what we're comparing to. So our null hypothesis is that mu equals 5, and our alternative hypothesis is mu is less than 5. So if we reject our null hypothesis, then we would think that the river would not be able to support aquatic life. Um, if we fail to reject, then we would say we failed to find convincing evidence that the river would have put aquatic life at risk. Again, notice we fail to reject. We don't say no, the river can support aquatic life. No, we fail to say that we don't have enough convincing evidence to say that it does put aquatic life at risk. All right. So and then this page kind of got screwed up in the notes, but basically what we got to do is we got to check that we meet the requirements. So um, we got a sample size of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm just going to punch the data in my calculator real quick. So I just put it all in list 1 here. All right, so I punched a bunch of stuff in my calculator. So again, I did it all under stat edit, put it all in my list 1. And now if you go to stat plot 1, I'm just going to look at a more or less a bar graph histogram. I'm going to look at that histogram and see if it looks approximately normal. Again, it's such a small sample size that I mean it looks doesn't look normal, but I mean it looks reasonably normal. And now if I go to and how did I do that again? I went stat plot. So second y equals gives me the stat plot. Plot 1 did my histogram there. X list was a 1. So let's turn that off and let's go to plot 2. Turn this one on. So this one I'm going to look at a box plot. So let's take a look at that graph. And there I have it. That looks slightly left skewed, but not too bad. And then finally, let's go back in the stat plot and let's look at the normal probability plot. So we want this last one to be approximately linear. So let's turn this one on. And let's look at, let me adjust my window here. Let's see here. I'm in 0, let's say. I think this should do it. So we look at this, and it looks, approximately linear. So I think we meet the requirements. Now again, on the AP test, you can actually do this on your calculator, but you can't just say looking at them on the calculator. You should draw a quick sketch. So you can draw a quick sketch of you know like and then and so well, and you don't have to connect that line, but just draw probably a little bit better than what I did here. But I don't want to waste your time while I draw it. Just a quick sketch. Maybe have your scales and label them and everything like that. So um, like I don't know, do level milligrams per liter, and then have your scale. Um, one, what was this, like 4 or 5? So something like that. Okay. So, anyways, now let's if we let's do actually do it. They have a screenshot there, but let's go ahead and do take a look at this. Let's do oops, stat one var stats. Oh, and then my calculator moved here. Do do do. All right. So we get that screen right there. Same idea there. All right. So looking at that, notice what we get for our sample standard deviation, 0.9395. Um, I guess 9396 if I round properly. And then X bar was 4.77, 4.771. And then we need mu now, again, when that was given, we assume that that was 5. Right, that's the threshold. So, anyways, we go through in this and we plug it all in. We get our t statistic of negative 0.94. So again, our sample size was 15. It looks like so. Um, so our degrees of freedom is going to be 14, and we're going to look for where does the area in that table equal negative 0.94. So we find df equals 14, we go across till we find negative 0.94, and we see it's got to be between 0.2 and 0.15 for our p-value. So at an alpha of 0.05, if we're between 0.15 and zero point 0.2, we would fail to reject the hypothesis. So we did not find convincing evidence that there is less than 5 oxygen level, dissolved oxygen level of less than 5. So again, you might find that kind of strange that we did not find convincing evidence, given that our mean was below 5 at 4.771. But again, that there's a reasonable chance, between 0.15 and zero point 0.2, there's a reasonable expectation that that might happen, even if the stream has a average dissolved oxygen level of above, like the actual population, the whole stream has a value above 5. Alternatively, again, if you want to find the exact value, we could do the TCDF. So we go to distribution, TCDF. Lower is basically we want to know less than that. So I'm going to say negative 1 E99 to negative 0.94. DF is still 14. Paste. And I get 0.1816. So again, we fail to reject. Oh yeah, and then the last question asked was what kind of error could you have made, type 1 or type 2? Remember, fail to is type 2. So the error we could have made is that we could have failed to reject when we should have, and that means that the that it could have that the stream does actually have a value less than 5 milligrams per liter, but we didn't find convincing evidence. All right, so similarly, we could just do all this right off the bat. Here it talks you through it, but let's just go ahead and actually do it. So I could go to stat, tests, just like we've done z-test and one prop z-test. We did that the other day. We could do a t-test. We have our whole data. If it just gave us like the sample statistics, the like S sub x and n and all that good stuff instead of the actual data, um, then we would use stats. But we're going to leave it as data. We said mu naught was 5. This is L1, frequency 1. We want to know that the mu is less than mu naught. So we do this. Notice we got this p-value. Sorry, I didn't mean to. But without any rounding, it's pretty close and everything like that. But so our p-value was 0.181 or 1809. Um, you notice we have our test statistic t at negative 0.94, and so we get all that information. So, and then notice this AP test right there. But don't just plug it all in and go. Make sure you explain what you're doing on your calculator. All right, so in 9.2 we talked about how similar um, two-sided tests were with confidence intervals. Well, the same thing happens in when we're talking about the sample mean in the calculations. So basically, look at these formulas. If I compare these two formulas, if I solve this for mu naught, basically I end up with um, this guy gets moved over to this side, that guy goes over. I end up with x bar minus t times sx over square root of n. Well, what that looks pretty similar to what we got right here, right? So it's just plus or minus, and it's a t star instead of t. But the idea is that they're very, 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 very similar. Um, Basically the same formula. Um, and so a two-sided test at a significance level alpha is the same at basically gives very, very similar information to a confidence interval at so like if alpha is zero point 0.1, 90% confidence. If alpha was 0.15, an 85% confidence interval. So that's what this 1 minus alpha talks about. But they give very, very similar information. So if the two-sided significance test rejects the hypothesis, then the confidence interval for, again, if it was alpha was 0.1, then this would be a 90%. If alpha was 0.05, this would be a 95%. Confidence interval will not contain. If it fails to reject, then the confidence interval will contain it. So very, very similar information. All right, so just a few more examples here. So we talked about that pineapple uh, company. They put in a new irrigation system. So the mean weight last year was 31 ounces. A different irrigation system was installed in the field, and they want to see um, if the irrigation system caused a difference. So here we have our information. We found the new mean is 31.935, and with the standard deviation and everything like that. So let's go ahead and figure out whether the it's we have convincing evidence or not. So let's use alpha equals 0.05. And again, you get to pick, but alpha equals 0.05 is a good spot to start. Like generally speaking, for on the AP test or whatnot, there's probably alpha equals 0.05 will work if they don't tell you what we have. Um, so we're going to use the one sample t-test. So we check whether it meets the requirements. Um, Random sample, great. We have to assume that there's more than 500 pineapples in a large field. Um, and then uh, we don't know whether it's normally distributed, but we have a large sample size, so it's okay to use t procedures. All right, so, and we know x bar is equal to, right, we got x bar is equal to that, s sub x is 2.394, and we can plug it all into our formula for our test statistic. Don't forget, why do we use 31 there? Again, that's what we're comparing it to. That was last year, so that 31 ounces, we want to know if we have if it's likely that our mean was that again this year or not. So it comes from this guy right here. And then, so we find the p-value using 49 degrees of freedom. Now again, if we're using the table, we have to use df equals 40 because there is no value for 49. We don't, even though 49 is closer to 50, we have to go on the side of caution. All right, so but alternatively, we could use the calculator's t-test command, right? So stat tests t-test. This time we have the stats. So this is 31. X bar was 31.935. S sub x was 2.394. N was 50. And we want to know the likelihood that it was more. All right, let me just double check. Actually, no, we want to know the likelihood that it had changed, not that it was more. So the fact that it changed would be this guy right here. Calculate. And so notice we get our test statistics of 2.76, p-value 0.008. And so at an alpha level of, remember our alpha was 0.05, this is less than alpha, so we would conclude that uh, we would reject the hypothesis, um, and we have convincing evidence that the mean this year is not 31 ounces. So, part B, can we conclude that the different irrigation system caused a change in the mean weight of the pineapples produced? Fill in your answer. So again, remember, in order to conclude that like cause and effect, remember it needs to be a well-designed experiment. So we would have to, have two things, two we'd have to compare two sets of data that are, very similar, where the only tangible difference between them is whether it had a new irrigation system or not. We don't have that, so I would say no. We cannot conclude that the different irrigation system, the weather could have been different, the soil could have been different, those types of things. So I would say no, we cannot. Let's see what the book says. No, it was not a comparative experiment, so we cannot infer causation, right? So same, basically what I was just saying. All right, so last little bit here. Comparative studies are far more convincing than single sample investigations. So for that reason, one sample inference is less common than comparative inference. Studies involve making two observations on the same individual, or one observation on each of two similar individuals, result in paired data. Remember, we talked about this matched pairs experiments back in, I don't know, chapter 5 or something like that. All right, so we can make comparisons by analyzing the difference in each pair. So these methods are sometimes called paired T procedures. All right, so researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers, um, and basically each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. And during the 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which they took caffeine and placebo was randomized, as we talked about in the matched pairs experiment. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers want to know if being deprived of caffeine would lead to an increase in depression. All right, so here's a table of the data. Notice what we're going to be looking at here is the difference: placebo minus caffeine. So why did the researchers randomly assign the order? Well, again, if everybody used the same order, then and it was all on the same time, there would be a lot of other potential random variables that would play a role. So one example would be like if the first 2 days were nice and the next 2 days were overcast and gray and rainy, then that might skew the data. So all right, so carry out a test to investigate the researcher's question. So we would expect the actual mean difference in the depression scores to be 0 if there was no effect. Therefore, we want to test this hypothesis. And we again, alpha equals 0.05 is a good spot to use if there's no significance level given. All right, so conditions are met. So is it random? Yes, we talked about it. It was randomly assigned. 10% condition. We aren't sampling without replacement or anything like that. So there's There is no 10% condition. And here's a nice example of the sketches I was kind of talking about. If you draw these sketches from plotting them on your calculator, um, but basically, again, this this example will show you the latitude you have. Like there's nothing. If you look at the data, there's no um, there's no crazy outliers. We got right -1 is seems to be on the small side, but we got 1, 1, and 3, so that's not that big. 19 and 18 are a little bit on the large side, I guess, but um, uh, those might throw it off a little bit. But you can kind of see the latitude in this. Just make sure you analyze and say, well, yeah, it looks approximately normal. This is not very linear, um, but T procedures should work pretty well. All right, so um, we put in all basically you put in all this data. Again, the right column, put all that into your stat list. Do your t test, and you can get this information here. And um, because the p-value is so small, it's smaller than 0.05, we reject the null hypothesis, and we think that caffeine does have an effect on depression score. Last little bit here. Um, this example here, it basically goes through and I actually want you to try it yourself. Read the activity on page 590, and if you go to the website, you can actually go and play with the same tools that we've played around with before. So it tells you to go to the website and play with an applet. I recommend you do that. Um, Finally, couple things. Sometimes something might be statistically significant, but it's pointless. It really serves no practical effect. And be aware when you're doing a bunch of tests on a bunch of data. We'll see why here in just a second. So here is the examples that showing that statistically significant does not mean important. Is um, basically we know from previous research that with no medication, the mean healing time is 7.6 days. The claim we want to test is that formulation NSB healing. We will use a 5% significance level. So we do a random sample. We find that the mean healing time for these students is 7.5 days. Standard deviation is zero point 0.9. You run through everything. You do a t-test. You find out the p-value is 0.04, and that so it is convincing that the mean healing time was less than 7.6 days. But we ended up with a mean average healing time of like 7.5 days, which doesn't really matter whether your wound heals in 7.6 days or 7.5 days. Not really. So while it's statistically significant, that does not mean it's a significant development, right? Statistically significant just means like, is there an evidence that it's less than 7.6? Yes. It doesn't have to mean it has to be significantly less than 7.6. It does not. Finally, this is I like this example a lot. Might the radiation from cell phones be harmful to users? Many studies have found little or no connection between using cell phones and various illnesses. Here's a part of a news account of one study. A hospital study that compared brain cancer patients and a similar group without brain cancer found no statistically significant differences between brain cancer rates for the two groups. But when 20 distinct types of brain cancer were considered separately, a significant difference in brain cancer rates was found for one rare type. Puzzlingly, however, this risk appeared to decrease rather than increase with greater mobile phone use. So, in this case, notice we did 20 different comparisons, right? 20 different tests, rather. And so, remember, at a 5% significance level, we would expect one of these to be significant just by pure random chance, right? So, uh, when we run one test with alpha equals 0.05, that's reasonably good evidence that you have found something useful. But running 20 tests and reaching that level once is not. Even if there was absolutely just completely unrelated things that we were studying. If we did 20 different tests on that, we would expect one of them just by random chance to have show some significance. So um, you would have to have a much a smaller alpha to say you have found something if you doing multiple tests like that. And that concludes this chapter.